Hello, London! Have you had a good week?
Yes.
Are you absolutely exhausted now?
Hell yeah.
Brain just melting down from Scott talking to you about immutable state flowing through monads and whatever else Scott talks about. So yes, welcome to the last talk of the conference. I believe they now actually refer to this as the Rendle slot. They've always put me on in the last slot because I do these talks that are not particularly intellectually demanding, and I'm not trying to teach you anything. I'm just kind of going, oh, look, I found this, it's cool. And then eventually they got to the point of saying, not having any other talks on at the same time, and it became a de facto keynote or lock note, as they call it, which is lovely. So yes, I'm Mark Rendle, very old and experienced software developer and relatively new bassist. And I am going to talk to you about how JavaScript happened. And if, from that title, you want to infer, and how can we stop it from happening again, that's fine. But no, we're going to look at all the programming, well, not all the programming languages that came before, because that would be like a 2-day workshop. But no, we're going to look at where various things that we kind of take for granted in programming languages came from along the way. And we're not going to be mean about any of them, and I'm not really going to be mean about JavaScript. And as I was researching this talk, I came across this quote, which I think is something we should all remember. Flon's axiom: there does not now, nor will there ever exist a programming language in which it is the least bit hard to write bad programs. Over the course of my career, I think I have worked with probably 30, 40 different programming languages, and Flon's right. I've written terrible code in all of them. No, so yes. So, hard to believe though it is now, there was a time when there were no computers and no programming, and we all had to have like proper jobs working in fields and factories and horrible places. And this went on for thousands and thousands of years. And then finally, in the 19th century, some people thought, oh, I know, wouldn't it be good if machines could do more of these things, more of this thinking stuff for us? And so this person came along. Somebody has actually already done a talk at this conference about this young lady. And this is, of course, Ada Lovelace. And Ada Lovelace was the daughter of the Romantic poet and European syphilis incubator, Lord Byron. And so Ada's mum thought, what's the best thing I can do for my daughter? I'm going to keep her the hell away from her dad. And so she got private tutors, and Ada was educated by these people. You all right there?
Yep.
Yeah, good. Okay. And she learned maths and she learned languages, and she became a very accomplished young lady. And she went to salons in London. Salons were places where clever people went to go and be clever at each other and discuss ideas. And at one of these salons, she met Charles Babbage. And Charles Babbage was in the process of building the difference engine, but had gone back to Parliament and said, oh, I've got a much better idea for a new calculating engine, which will be even more powerful. And he built a prototype of like one set of rotors of this. And Ada talked to him about it, and he explained how it would work, and she understood it. And then she was translating a book written by an Italian about Babbage and his engines. And in the process of doing that, she wrote a program for the calculating engine to calculate Bernoulli numbers. Now, Bernoulli numbers, I haven't got the faintest idea. But this is a program to calculate Bernoulli numbers. And so this is essentially the first computer program. The computer that could run it was never actually built. And Ada died before any of this stuff. She died very young, actually. It's tragic. And then from the mid-19th century up until the sort of end of the first half of the 20th century, absolutely nothing happened at all. Nothing. Nobody built anything interesting in that time. And then we thought, we're bored, let's have a war. And so all of Europe went, hey, and started charging at each other in tanks and that sort of thing. And the Nazis, it's very important to say the Nazis and not the Germans when you're doing this, so edit point. The Nazis were very good at war, and they were very organised and very good at sort of planning things and so forth. And they would share their plans using one of these. This is the Enigma machine. And they used this to encode messages and send messages around, and we just had no idea what they were talking about. But a guy called Alan Turing came along, and building on the work of some Polish engineers, he built this. This is a bomb. And this can calculate or test multiple combinations of Enigma machine dials all at the same time. But it's not really a computer. It's just a machine that goes, ka-chunk, is that right? Ka-chunk, is that right? And it's doing that on lots of dials all at the same time. But it was a machine, you built it, and you turned it on, and it did something, and then you turned it off again. So it was like a computer, but not programmable. And then the Germans came up with this little bugger. This is a Lorenz cipher. Incidentally, fun point about the Enigma machine. So we cracked this using the bomb, but there was this whole thing about we can't let the Germans know we've cracked their code because they'll stop using it. And so we had to act as though we hadn't cracked it. And we actually had to let some terrible things happen, because if we had stopped them from happening, the Germans would have suspected that we knew their codes and so forth. That's not the interesting bit. The interesting bit is that we didn't tell our allies that we'd cracked it either. I think the Americans knew, but the Canadians and the Australians and New Zealand and all our other allies, we didn't tell any of them. And then when the war finished, and we'd captured all the Enigma machines off the U-boats and everything else, we went to all our allies and we said, hey, we should communicate using these, it'll keep stuff completely secret. And then we spied on our friends for like 40 years until the Official Secrets Act expired. But yes, anyway, the Germans switched to this thing. This is the Lorenz cipher, and this is so much more complicated than the Enigma machine. So the Enigma machine has trillions of possible combinations. The Lorenz cipher has more possible combinations than there are atoms in the observable universe. It's a lot. And we never captured one of these, but just from studying the way it encrypted, studying the actual encrypted text, British cryptanalysts were able to deduce how the machine worked. And they got it exactly right. So yeah, they figured it out 3 years before they got their hands on one, and then when they did, they went, oh yes. But yeah, this was much more complicated, and so we needed to build something more complicated to crack the code. And so Tommy Flowers, who was a man who worked for the post office on telephone exchanges, built this with Alan Turing and a bunch of other people, and this was the first programmable computer. This was Colossus, and you could put different programs in it and it would run them through. It was still very much a kind of create the program, connect the machine up with the program wired in, turn it on, wait, it does it, and then turn it off again. But it was programmable. When the war finished, we smashed all these to pieces because they were all covered by the Official Secrets Act and we didn't want anyone to know we had them. And so that is why the Americans think they invented computers. But they didn't. But this was the computer that the Americans invented, ENIAC, the Electronic Numerical Integrator and Computer. And it's important to remember that at this point in history, computer was still a job title. Computers worked at the Army and Navy and Air Force, calculating trajectories and all this sort of thing. They worked at NASA. And so, yes, and most computers were women, because who knew? Turns out women can do maths too, right? Wow. And so they needed people to program the ENIAC. And you can see 3 people in this picture programming the ENIAC. And programming the ENIAC meant patching cables from there to there, and from there to there, and so on and so forth. And so these are the ENIAC programmers: Kay McNulty, Betty Jennings, Betty Snyder, Marilyn Westkoff, Fran Mielis, and Ruth Lichterman. All women. And the primary reason they were all women, so they were all good at maths, and also they had worked on telephone exchanges during the war, most of them, and so they were very good at this whole switching cables around and everything. But there was no documentation for the ENIAC. The men who built it hadn't bothered to say, this is how it works. And so the women had the kind of blueprints of the thing, and they worked out how to program it. And yes, so that was the sort of state of things for the 1940s, late 40s, early 50s. And then IBM came along, and IBM had been building essentially very big calculators for a very long time. But IBM came along and they built the 701 mainframe. And you could use this to run complicated mathematics formulas, and you would program these in. But this is the formula for calculating trajectory. So y is x tan theta minus gx to the 2 over 2v to the 2 cosine 2 theta. Yeah. See, I don't even understand that. I have no idea what's going on with that. But you couldn't just put that into the computer. You had to convert this into machine code. So you had to go, right, so if I need to do a cosine operation, then that's put this value in a register here and put this value in a register here, and then multiply those 2 things together and then put that back into memory and then get some... And you had to be able to work out how to break it down into all those steps. And that was what programming was like in the mid-1950s. And then this chap came along. This is John Backus. John Backus was just wandering down the street in Manhattan one day, and he passed IBM's offices. And he looked through the window and he saw the IBM 701 through the window, and it had all the flashing lights and everything on it. And did you know, by the way, that the flashing lights on all those mainframes from the sort of 50s and 60s, mainly marketing. They did sort of technically indicate some internal state of the computer, but mainly they were there to flash on and off and make the C-suite think, oh, I want one of those. But so John Backus saw this and went in through and said, oh, what's that thing you've got there? And they said, that's a mainframe computer. And he went, can I get a job working on it? I really want to work on that. And they went, yeah, go up to the 5th floor and do an interview. And they did, and he got the interview. And then he started working at IBM as a programmer. And then they showed him all the machine code and everything else. And he thought, there must be a better way. And the reason he thought that is because John Backus was essentially a lazy bastard. He did not want to do the work of figuring out how to translate the formula into machine code. You know, I've got the most powerful machine mankind has ever built here, and so why can't I get that to do the work of translating formulas into machine code for me? And this is why lazy people are such a valuable resource for humanity, because lazy people find the easy way to do everything. And I'm pretty sure that as software developers and engineers, that's a pretty big part of our job title. It's make stuff easy for other people. And the lazier we are, the better we are at doing that. And so John Backus, having just started at IBM, hasn't been working there very long, goes to his boss and says, I want to write a piece of software where we can just put in the formulas as like text, and it will automatically generate the machine code for you. And his boss went, yeah, all right, grab a team, find an office, crack on. Because IBM in the 1950s was apparently very different from IBM now. Because if you went to IBM now and I want to build it, then right, well, we'll schedule a meeting for 2026. So he got his team together. This is part of his team reuniting at a conference much, much later. And over the course of 3-4 years, moving around, bouncing around offices and different buildings and staying in hotels opposite offices and all this sort of stuff. And they came up with a system that would translate formulas. It was a formula translator. And in a fit of naming genius, they called it Fortran. And it was released in 1957. And this is FizzBuzz in Fortran. And so you can see here that there's some stuff that we're already recognizing. Okay, so we've got a loop there. We're not using for loops yet. So we're saying do 40, I equals 1, 20. So that says do everything down to line 40 for the numbers 1 to 20 and put those into the variable I. Why I? Because Fortran had 2 data types, integer and real, or floating point. And the way that you declared a variable as being an integer variable was you made its name start with I, J, K, L, M, or N. If the variable started with any other letter, it was a float, it was a real. This actually did change in fairly quickly. You could specify the types of your variables. And there's an old Fortran joke, God is real unless declared integer. I didn't say it was a good joke. So yes, what this is doing is we're saying, okay, so start here, the loop ends at 40. And we're going to assign one thing, and then we can say if mod I15 doesn't equal 0, then go to 20, skip the next 2. Otherwise, print asterisk, comma, 8h FizzBuzz. So strings are prefixed with 8h. Anything after 8h will just be taken as text. And then continue, so go back up to the do. Otherwise, we go to 20, and if it's 5, then if it's not divisible by 5, then we go to 30. If it's not divisible by 3, then we go to 40, and then down at 40, we just print whatever the number is, and then end loops us back up to the top of the do. And so we have loops, and we have something like a for loop. We have if statements, and we have goto. I like goto. I know everyone goes, oh no, you mustn't use goto in your code. But the fact is, sometimes it is the best way to exit yourself out of 3 or 4 levels of nested loop. And also, if you compile your code and then let the JIT compile your code and then look at the actual generated machine code, all your precious structured programming with your loops and your conditionals and everything else, you know what those compile to? Goto. So, I'm just a low-level programmer. So, yes. So on this, we have if statements, we have this concept of loops, we have line numbers, we have gotos. And this is the other interesting one, is the original version of Fortran, before they got to the point of people trying to type programs in, so they were just writing the programs on punch cards across the top and then punching the relevant characters in. But when they got to the point of typing these in on punch card typing machines, they had been using the times symbol, which is not an X, it is the times symbol. It's got its own Unicode point now, didn't then. And the machines that they were typing on didn't have a multiplication symbol. They had slash for divide and they had plus and minus, but they didn't have times. And so they went, okay, what's the nearest thing to times that we've got on there? And they decided it was the asterisk. And so that is why we still use the asterisk for multiplication. And I just think that could have been anything. They could have made any choice at all, and we'd be going, oh yes, no, the @ symbol is what we use for multiplication, and then we'd all be using asterisks for our Twitter handles. So yes, the X was replaced with the asterisk. And Fortran, this is a Fortran statement card. So it's got 80 usable columns, plus a few kind of error correction and everything else. And every one of these cards was a single line of code which of course meant that no line of code could exceed 80 characters. And to this day, a lot of editors will come with the word wrap set at 80 characters. And it still dates back to punch cards. When they introduced teletypes and terminals with screens, they were 80 characters wide because punch cards were 80 characters wide. Completely arbitrary. If punch cards had been an extra 40 columns wide, then everything would be 120. But no. So Fortran, the if statement, the asterisk for the multiplication operator, and I as the iterator variable. Because if the only rule you've got to follow is the variable name must start with I, blah, 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 then you immediately go, I'm just going to call it I then. Fine, we'll use I. So that's where we get that from. And then this chap came along. This is Edgar Dijkstra. And he said a lot of things about programming over the course of his career. The one that we're worried about here is goto considered harmful. He did not like all the gotos. He thought that was chaotic. And, you know, he's got a point. When it was the only way of doing control flow, not a plan. It's just useful in a few occasions. He also said some other stuff that's brilliant. If debugging is the process of removing bugs, then programming must be the process of putting them in. There you go, use that in your job title. He also said something about BASIC causing irreparable brain damage. He did not think people should learn BASIC as a way of learning programming. Any VB people in the room? Nobody, oh, there we go. It's a perfectly cromulent language. So yes, and he made this fuss and said we need structure in our programs, we need a way of structuring them and making them sane. And so a bunch of people got together and they created Algol. And Algol, the first version of Algol came out in 1958. You cannot write FizzBuzz in Algol 58 because the key feature of FizzBuzz is that it must print FizzBuzz, or a number. And the one thing that Algol 58 did not have was output. So yes, you could run an Algol program and then check the contents of the memory register at the end, and that's where your answer was. Didn't have a way of doing print. Algol 60, I think, added it. But so this is FizzBuzz in Algol 60. So we say begin and integer I, and then for I colon equals 1, step 1 until 100. It's very readable. It's one of those languages where you can kind of, even non-programmers would be able to come along, and if you explained what %* did, which is obviously modulus, then that would work. And then you've got this outstring thing there. But you can see, instead of Fortrans having the 8H before strings to mark them as strings, we put them in quotes. So Algol brings us that idea. And we have for as our looping construct for the first time. So we say for each of these things, do this thing here. And also semicolons at the end of the statement lines and not at the end of the control flow lines. So Algol was created by a committee of people, and John Bacchus was actually on that committee, and he came up with a way of describing the structure of a programming language, and he called it Bacchus normal form. And it looks something like this, BNF, and we still use this to this day. Nobody's really come up with it. People come up with other alternatives, but they are essentially variations on this theme. There was another guy on the committee who, I've forgotten his first name, but he was called Nor, and he suggested some modifications to it, and so actually what BNF stands for now is Bacchus Nor form, because somebody said, we should take the normal out and just have Nor instead, and then you can both have your name on it. So yes, but we still use this to this day. There's for loops and iteration statements and everything else. And so we get quite a lot from Algol. We get this idea of block structure, begins and ends and that sort of thing. We get if, then, else. So Fortran had if, and then the else was basically go to. But ALGOL had switch, so switch something, case, 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 case. It had for loops, it had functions. It was the first thing with the semicolons at the end, and they created the grammar that we still use to describe programming languages to this day. It never ever took off. Nobody really liked ALGOL. Nobody used it to build anything of any significance. All the mathematicians still liked Fortran, and we'll see what everybody else was playing with in a moment. But just taking one brief detour into, there were a lot of ALGOL variants. There was a lot of research done in the ALGOL space, and one of those was ALGOL W. And ALGOL W had records, or objects, like structs, an early version of OOP objects. And once you've got records, if you've got numbers, you say, what number goes in here? Well, it's 1 to 52, whatever it is. If you've got records, and so you've got a person record, and then there's a spouse field in that person record, and you're having an unmarried person, what do you put in the spouse field? And they didn't know, didn't have any better ideas, and so Tony Hoare invented null. And yes, we are still dealing with that to this day. So yes, there you go, there's some ALGOL W. There's a record with 3 integers in it and a reference R, and then we assign null to the reference. The billion-dollar mistake and counting. What other people were doing over at MIT and places like that, they were working with Lisp. So Lisp was created by John McCarthy. And John McCarthy was a student at MIT and then doing postgrad work at MIT, and they were looking at artificial intelligence. They had very quickly come to the idea that computers would be able to think just like people could think. And their best approximation for how people think is that we have lists of stuff and we work out correlations between lists of stuff, and that is how, and so they modeled that in a programming language, a list processing language, or Lisp. And this is FizzBuzz in Lisp. And let's sort of, do I have a pointy thing? No, never mind. So yes, we define a function called FizzBuzz, and then we say loop for n from 1 below 101, do, so exclusive. And then we declare another couple of functions, divisible by 3 and divisible by 5, and then that returns true if the result of the calculation is 0, and then we put a cond in there, which is Lisp's equivalent of a case statement, and then we say if it's both these things, then we do FizzBuzz, otherwise we write this, otherwise we write that, otherwise we format it like this, and then we close all our parentheses at the end. Has anyone ever actually written production code in Lisp? It's what rainbow brackets was bloody invented for. You're just like putting in brackets until you go, it's red, yes! Commit, push to GitHub, run away before anyone does a code review. But yes, Lisp was basically the first functional programming language. It was the first thing where we threw functions around, it had first-class functions, all this sort of thing. And another fun aside, so those of you who have done Lisp, car and kudru. Yeah? Really weird. If you want the first item off a list, it's car. If you want the rest of that list, it's kudda, because in Lisp, lists are linked lists. And so yeah, car and kudda, not head and tail or head and rest or anything like that. Car and kudda. Still, I think Clojure even supports using car and kudda to do this. And people go, what does that stand for? So, the IBM 704, which was what Lisp was built on, had 36-bit registers. Nobody had kind of standardized on let's do multiples of 8 or powers of 2. It's just kind of like, how many bits seems convenient? Let's do 36. And you had an address register, so the second half of that was an address register. The first bit was a decrement register, and then you had a couple of spare bits here and there for some other things. And so when you were making a linked list, you put the value of it into the address register, and you put the pointer to the rest of the list into the decrement register. And so car and coulda, Lisp people, stands for content of address register and content of decrement register. And if there's ever been a better example of an implementation detail leaking into the user interface for something, then I have yet to see it. But Lisp, I mean, there are people who love Lisp, and there are variants of Lisp going on to this day. It's an interesting language to learn, and worthwhile. It does teach you some interesting things. But Lisp gave us first-class functions, the idea of a function being also an object that you can pass around and pass into other functions. It also was the first programming language with a heap, because if you remember, I just told you, the decrement register contained a pointer to the next item in the list. And so that pointer is pointing to a space on a heap. And so Lisp was the first language with a heap to allocate variables on. And once you've got a heap, you need garbage collection. And Lisp, even back in 1958, Lisp had a garbage collector. Count the references that were being held to something, and if there weren't any, it would clear out the heap. It even had a sort of primitive JIT. So Lisp was interpreted, but it was the first place where something resembling a JIT was included in a programming language. It would do some optimization if it had the opportunity. Algol, meanwhile, evolved, was the basis for Simula. And Simula was the first object-oriented programming language. It was created at the University of Oslo, or it was in Norway anyway, so very NDC relevant. But yes, Simula was the first language to introduce the idea of object orientation. Not Smalltalk, as people often think, Simula. So this is FizzBuzz written very badly in Simula, and you can see it's kind of algol, because we've still got colon equals for assignment, we've got the semicolons at the end there. Outstring has become outtext, but it's pretty much the same thing. It's just now we've got new and inventive ways to make our code much more complicated, because we can put all the stuff inside there into a class printer, and then we say ref printer p. P is a new printer with 3 fizz, 5 and buzz, and then we can just call p.print. And the advantage here, obviously, is that you're passing in the numbers and the words that go with those numbers to the class, and then they become part of that class's state. And so you can change the behavior by constructing the class differently. So this is where object orientation reared its ugly head. And from Simula, we took classes and inheritance, polymorphism, so you could inherit, one class could inherit another class and then override some of its behavior. So we had polymorphism, and also the idea of scope for members of a class. So private, public, protected, that sort of thing. And then this happened. Has anyone written code in APL? Or KQL, that's kind of similar to APL. But yes, APL was created in 1967 by this chap, whose name completely eludes me all of a sudden. Yay! Probably early onset Alzheimer's. Kenneth Iverson, that's it. It's just written in squiggly text. And he taught programming. And he didn't want to teach programming using BASIC, he didn't want to teach programming using Pascal or Algol or Fortran or whatever. He wanted to reduce programming to purity, the purity of communicating your thoughts and intentions to the machine. And so he created his own programming language, which he called APL, which stands for a programming language. Have to meet his kids, son and daughter. So yes, this is FizzBuzz in APL. I have no idea how that worked. I did know how that worked. When I actually made this slide, I knew how it worked. It's gone. It does not, APL does not stay in my head. The thing about APL, though, is that it works on arrays like all at the same time. So you don't have to say for I equals 1 to array.length, do something. You just go, do this to everything in that array and put the results of that into this array over here. And so what this doesn't print anything, I don't think, but it does take an array of numbers from 1 to 100 and then run a single operation, which then you have another array which contains fizz and buzz and FizzBuzz and numbers. And it's a single line of code. And you may notice some things in this that would make it a little bit hard to type. That's not a lowercase w. I don't know what that is there in front of those ones and those two. There's an umlaut that's lost its O, which is just a tragedy. But yes, things that are not on a normal keyboard. It had stopped the Fortran people from using the multiplication table, but it didn't stop Kenneth Iverson from using most of the Greek alphabet and some ink splatters that he thought were a good idea. And he threw them all in there. And so if you wanted to do Kenneth Iverson's course on programming, you had to buy a keyboard. This is an APL keyboard. And yes, also no. But yes, you had to, and today people actually still write APL code, and there are sort of shortcut versions of the things, but there are still people who have APL keyboards and are writing useful code in them. I mean, you know, that's FizzBuzz. You think that's quite impressive. That is not what it's supposed to be. I've copied and pasted a slide and buggered up. Somewhere I've got Conway's Game of Life. It's actually shorter. It's just squiggles. There's nothing recognizable in there at all, but it's the whole of Conway's Game of Life in a single line of APL that looks like it would probably decrypt and translate into the location of Caesar's tomb. But APL had dynamic types, so that thing of having an array and putting fizz and buzz and numbers into it, it didn't have the concept of variables having a type. So you could have, it was an array of things, and you could put numbers in there, you could put strings in there, you could put booleans in there, you could do whatever you liked. And so we have APL to thank for dynamic typing. Over in the sort of more sane part of the world, and throughout the 1960s, we had B and BCPL, batch control process language and control process language. And so these were sort of iterating on Algol and trying to turn it into something usable. And so this is FizzBuzz written in B. And you can see at the top there, it's starting to look quite a lot like C at this point. We've got get lib header, so that's like an import thing at the top there. And then we say, let's start B, because that's a lovely way to define a function. It's like, let this be something. It's like very John Lennon, or possibly Captain Picard. So we let start be this function, and then we essentially have something resembling. Although for some reason we've decided, no, let's not use if, let's use test instead. That's a much better way of wasting 2 extra characters on every line. This is still at a time when those 2 extra characters, it's like when a bit of memory cost like 10 cents. So yes, they obviously had money to burn over at Bell Labs. But other than that, looks pretty much like Algol, all that sort of thing. We have write s to write a string and write n to write a number. We've got rid of the semicolons at this point. We don't like the semicolons. But the other fun thing, so remember the times symbol wasn't on the keyboard? Curly braces also were not in the 7-bit ASCII standard that existed at the time that this was created. It was added in fairly quickly after this, but it did not have curly braces. And so if you were working with that sort of proto-ASCII that didn't have them, then you could just use $, and normal parentheses instead. It meant the same thing. So BCPL gave us curly braces, even though most people at the time couldn't use the curly braces because it wasn't in the character set that they were working with. But it had them anyway. And of course, BCPL eventually, in 1972, became C, the first and last language that anybody ever needed. So C was created to build Unix, which was a joke operating system. So the people who made Unix had been working on something called Multics, which was an absolute disaster, one of those famously disastrous software projects. And then they went, let's make a sort of simpler version of this, and we'll call it Unix, and it's just a bit of a joke. And they were, what language are we going to write it in? And I'm pretty sure they went, oh, let's make a joke language, and we'll call it C, where approximately 50% of the things that you can type cause undefined behavior. And then we'll write all about it in this book, which I learned programming from. And the C programming language by Kernighan and Ritchie, who worked on the language itself and on Unix, was the first place that in teaching you to program, the first thing it taught you was hello world. They invented the idea of hello world without the exclamation mark, with the comma, without the exclamation mark. So people who add the exclamation mark to hello world are exactly as sick as I has always thought they were. So yes, this is FizzBuzz in C, int, main, void, got an include up at the top there. And I don't really need to explain this because I'm pretty sure the majority of people are used to working with C-like languages, and that's what we call them. We call them C-like, C-style syntax. Curly braces, semicolons, that's a C-style language. So yes, but we have our for loop. This is where we get our for loop with the 3 sections, and the I equals 1, and I is less than 100, and I++. And actually still today, a lot of people, what they don't realize is that that's the simplest form of a for loop. You can put as many initializations as you like before that first semicolon. You can say I equals 1, j equals 2, p equals 7. And then you can put insanely complicated conditions, because that thing in the second section just has to be a condition that resolves to a Boolean. And then you can do whatever you like in that last bit as well. You don't just have to add 1 to I, you can read a record from a database. I've written some truly horrendous for loops. I once wrote an ISBN number validator for a friend of mine who was asking for help with their C++ homework. And so I wrote them the proper version of it, and then I reduced it to a for loop with a semicolon at the end. And they showed it to their teacher, who said, never ask him for help with your homework again. Because that's the great thing about C, is, yeah, you can write nice, clean, clear code like this to do FizzBuzz, or you can do this. Which, that's FizzBuzz, doesn't have, you can't find fuzz, fizz or buzz or anything in there, but that is FizzBuzz in C. And there's a competition every year, the International Obfuscated C Contest, where people compete to see who can write the most obscure C code, and it's people draw pictures and ASCII art that compiles and quines and all sorts of mad stuff. And other programming languages, obviously, some are better at this than others, but JavaScript, that's valid JavaScript. Dylan Beattie has a talk where he can explain why. And I beg you, please go and see that talk, because I can't explain why. But it's something to do with the type coercion. And so you can get like the O, B, J, E, C, and T out of the word object and then put them in. It's all very, very complicated. But that is apparently, I did run it in a console, and it does print the numbers from 1 to 100. But from C, we got what we now call C style. We got hello world as your first thing, and we got the idea of truthiness as well. So truthiness was the first one, C was the first language where you say, if Boolean, do something, and it would go, yep. If number, and it would go, oh, well, if the number's 0, then we'll call that false. Every other number in existence we will call true. The concept of truthiness, which is why you could write while C equals getchar when you're reading from standard input or from a file. So it would do the assignment and then say, the value of that assignment was not 0, and so we will carry on. So thank you, C, for truthiness. Thank you for giving that. And obfuscating code. The whole idea of obfuscating code came from C. Simula, meanwhile, had evolved 10 years later into Smalltalk. Smalltalk was created at the Palo Alto Research Center, also known as Xerox PARC. And Xerox were building the future of computing. They really were as well. They were building graphical user interfaces. They were building a machine that actually did have the screen layout was pretty much A4, or I think what the Americans call letter, because you're typing a document, what you see is what you get, and it makes sense to have it that way round. Don't know how we switched back to going, let's just keep making screens wider and wider. But yes, and so the idea, obviously windows are objects, buttons are objects, so it makes sense to use an object-oriented system for building a graphical user interface. And also we need a way to, because we're no longer sort of giving the user a choice and then waiting for them to make it and then reacting to that choice, we're basically giving the user a page and saying, you can do whatever you like. You can click this, you can click that, you can put the cursor here and you can type. And so suddenly we're responding to any one of an array of available inputs. And so Smalltalk introduced the idea of message passing, the idea that you could trigger functionality in an object by sending a message from another object, like the mouse or the operating system or whatever it might be. So this is FizzBuzz in Smalltalk. Again, not really going to dig into that too much, but there is we're extending the integer class. So Smalltalk enabled this idea of monkey patching. If you've ever worked on Ruby code, monkey patching is the thing that probably made you want to kill somebody. So yes, we are adding a FizzBuzz function to integer, and then we take in the FB bit here, and then we do something, and I don't know, and to 100, and so forth. But this then becomes a static FizzBuzz function on the integer class. Now, you ever sort of been in a JavaScript class or read a JavaScript tutorial book, and it talks about this idea of everything is an object? Everything is an object. Nan, that's an object. Type of nan, object. Actually, no, type of nan is number, isn't it? Anyway. But yeah, so this is from the Wikipedia entry. Since all values are objects, classes are also objects. Each class is an instance of the metaclass of that class. Metaclasses are, in turn, also objects and are all instances of a class called metaclass, which is an object. Code blocks, Smalltalk's way of expressing anonymous functions, are also objects. So yes, this idea of everything being an object that JavaScript has came from Smalltalk, but so did reflection. Smalltalk was the first language where you could reflect on the code, the type system and everything at runtime and change your behavior and pick up missing methods and that sort of thing. It was the first language that had a console for writing debug output to that would go to a separate window on the graphical user interface. It was the first system that had a virtual machine, so you could re-implement the Smalltalk virtual machine for a different CPU architecture and then run your Smalltalk code on that virtual machine. It was the first thing that had a proper JIT, although technically still not. So we had a sort of JIT in the very early version of Lisp, and then wherever we are with Smalltalk, I forget the date, 1972 with Smalltalk, we have a JIT, but actually there had already been a JIT implemented 3 years previously to Smalltalk. Guess what the first JIT was made for? It's regular expressions. So yes, somebody implementing regular expressions and went, these are slow, I'm going to compile this to machine code. And everything being an object came from Smalltalk as well. Honestly, not entirely clear what that is. And I have no notes on my slide. Yeah, no notes. That's just a mystery slide. Never mind. Okay, Lisp, functional programming, had evolved into ML at this point, and we still have ML with us today. ML became Camel, became OCaml, became F#, and you can trace a direct line through those. And you can sort of see that coming here. We have a fun FB str takes a value and then does a case against it, does this structural pattern matching that we've got here, which, as we all know, C# invented quite recently. Isaac, you in the room? And we have the equals greater than, the lambda syntax. This was the first language to use that equals greater than as a kind of goes to thing that we still use for lambda syntax today. So yes, ML gave us the arrow function syntax, and it did give us pattern matching as well. So pattern matching came from ML. It doesn't get mentioned because JavaScript doesn't do it. And we're only talking about, that's also why COBOL isn't in here. I'm going to do a whole other talk about the dead-end languages like COBOL that were such a bad idea that JavaScript, even JavaScript, hasn't taken anything from COBOL. Apart from maybe Angular. The other thing that came out of Lisp was Scheme, which was a very, very simplified version of Lisp, which Abel and Sussman created to teach their Introduction to Computer Programming 601 at MIT. And you can still, to this, you can download for free off the internet Structure and Interpretation of Computer Programs, which is starting from absolute first principles, using Scheme as the programming language, and it will teach you loops, iteration, recursion, all this sort of stuff. Doesn't even invoke the idea of mutable state until chapter 7. Objects are later on in the book. But yes, so Scheme, it's Lisp. It's just a simplified version of Lisp. Someone says implement a programming language as quickly as possible, implement a scheme. It's very, very quick. It's just, the parser is also, Lisp programs and Scheme programs are also just lists. So the syntax is also the data structure. It's very, very simple to build one of these things. And so actually what we get from Lisp and Scheme, but Scheme in particular, is the idea of being a scheme. Because when they went to Brendan Eich and said, write a language in 10 days, he went, right, Scheme. And he built it, and it was. He integrated Scheme into the browser. And then he took it to the suits, and they went, well, no, because we're competing with Java, so could you make it look more like Java? Because obviously, if you want to compete with something, you have to look like it. And so he went and he made his Scheme look like Java, even though under the covers, it was still basically Scheme. Up in the top sort of structured part of the world, C and Simula came together in an unholy alliance and formed C++. And I've taken the branch there from Simula rather than Smalltalk, because Smalltalk did object-oriented programming right, and C++ did object-oriented programming and everything else wrong, and is insanely popular to this day. This is the man who created it, and this is what he himself said about it. C makes it easy to shoot yourself in the foot. C++ makes it harder, but when you do, it blows your whole leg off. Hands up anyone who's ever blown their own leg off with C++. Yeah, com interop in C++. That won't just blow your leg off. That'll take out the whole floor underneath you as well. This is FizzBuzz in C++. This is the weirdest thing. I will never, when I sort of picked up the book, knowing C and being able to write sort of fairly complicated things in C, and it's kind of like, C++, he's just going to have added some stuff. No, now we no longer have printf and just pass some values to it. No, we have this less than. What is cout less than FizzBuzz? How is... I just don't even. So anyway, I'm going to move on. But yes, so from C++, we actually get the idea of exceptions. So C++ was the first language with exceptions and try and catch to do exception handling and that sort of thing. And so therefore we also get throw from there as well. So try, catch, throw, those were introduced in C++ to make it easier to deal with errors, because in C, you returned a value from a function, and generally you would return like a sentinel value like -1 to indicate that the function had failed, or you would return something, and then there'd be like a global variable set somewhere telling you what the error had actually been. So then the whole chart reorganized itself because I created it with D2, and it just lays it out the best it can, because I can't use graphics programs to do this sort of thing. And so now APL's suddenly up at the top and Smalltalk's gone there. Has anyone ever even heard of a programming language called Self? Blue-haired dude at the front, not surprised. But apart from that, no, I'd never ever heard of Self. Self was kind of, it inherited some stuff from Smalltalk, it inherited some stuff from APL. It was very, very weird. This is what it looked like. So it was designed and built entirely to run in GUIs on not Xerox machines, but Apple and that sort of thing. This is Self doing object-oriented programming. So we have an animal, which is just the empty object, and dog, which is, well, it parents to animal, and we can add some additional stuff to it. And these are not classes. So this is object-oriented programming, but these are not classes. They are prototypes. And so animal equals this, and then you can create an instance of animal, and it's basically just taking a copy of whatever's in animal. And so it's the alternative way of doing object-oriented programming, prototypal object-oriented programming, which, interestingly, if you want to do object-oriented programming in Scheme, is the only way to do it. And so Self uses this prototypal approach. So that is where we get prototype-based OOP from. Then down at the bottom here, we've got C++. 10 years later, that becomes Java. This is FizzBuzz in Java. You're welcome. Java, I think we can agree that Java hasn't introduced anything useful to the world at all, and we should destroy it with fire. So yes, the main thing that Java has donated to JavaScript was make it look like Java. It's like any other language, please. Well, maybe not basic, but yes. And then all of these things together, essentially, you get Scheme, and you get Self with its prototypal inheritance and so forth, and you get Java with its just generally looking a bit like C++ syntax, and all these things come together to make JavaScript. So and you can trace this through, and there's things in JavaScript that go all the way back to the very first programming language, Fortran. Incidentally, most of these languages that we've passed along this route are no longer in common use. Fortran, try and prize Fortran out of the hands of mathematicians and physicists who need to build complex models of like chaos theory and that sort of stuff. Still, nobody has come up with something that they've been able to say, don't use Fortran, use this. They go, no, Fortran. Every time Intel release a new CPU architecture with new CPU instructions, the first language to get access to those is the Intel implementation of Fortran. So SSE and SIMD and all these kind of massively parallel operations and so forth, they were in Fortran a long time before they were in GCC or LLVM or Microsoft C++ or any of those sorts of things. But of course, languages didn't stop evolving in 1995, fortunately, because otherwise we'd just be stuck with JavaScript. And other languages have been released since then, and languages which JavaScript has taken ideas from. And obviously, the key one of those would be C#, which came out in 1999 and was derived from C++ and not Java. I did this talk in Copenhagen at the Developer Festival last year, and Mads Torgersen was in the audience, and he roared at that. But no, because you can tell that C# is the successor to C++ because it's C++++, and you put two of the pluses under the other two pluses, and it makes a sharp symbol. That's why it's called C#. F# just copying, because there's no F++, as far as I know. But yes, and so C# introduced this idea of async and await and task-based programming, which became promise-based programming, but these keywords that you can actually put into your code. And so there are still innovations happening in programming language design, and we can only hope that more of those innovations make their way into JavaScript, like, static types. Wouldn't it be nice if TypeScript... Actually, I don't really want JavaScript to be TypeScript because you seem to need a degree in category theory to understand some of what the type system in TypeScript is doing these days. But it would be very nice to be able, in the actual language itself, to say, hey, function, only take strings, rather than having to start every function body with if type of thing is equals string, otherwise throw an invalid operation exception. But yes, so there you go, lovely people. I hope that wasn't too taxing. I hope you may inadvertently have learned one or two things, even if it's just a kind of coffee pub conversation. Did you know? But that's my little talk to finish off the conference. I hope you've all had a fantastic time, and I hope you will all come back next year and we can do it all again. Take care of yourselves, look after each other. Bye-bye.